I'm 50 years old, secondary 3 Friends High School. Here we have a lesson on physical chemistry. And we're taking a look at the Maxwell-Boltzmann distribution. Alright, in the previous few lessons, we had different things about the Maxwell-Boltzmann distributions, functions, and all. In this lesson, we will be looking at something a bit different, which is to show the ideal gas law. The ideal gas law, most of you might know what it is, since during physics lessons or chemistry lessons, depending on what kind of topics you learn, you could have heard of PV equals nRT a lot, or PV equals capital N kBT, alright? So, the ideal gas law is something that you would use a lot, but some of you might not know where did it come from. Well, you might have heard of, yeah, you can combine the empirical laws for Charles' law and Bohr's law to derive it. But is that all there is to ideal gas law? So in this time, we will be combining a few things with the Maxwell-Boltzmann distribution in order to prove the ideal gas law. Right, so if we're not going to use the Charles' law or the Bohr's law, how are we going to show it? Now, the things that we can use are of course Maxwell-Boltzmann distribution and your Newton's second law, so F equals ma, and you would have your pressure, which is F over A, your force over the area, alright? So, let's start this thing. Now, ideal gas law. Let's start with the most basic case, which is a singular particle within your entire container that you have. So, this singular particle, let's say it is moving towards the x direction in order to collide with this surface or with the container, alright? So it collides with this container. Let's just say we only take one collision first, since every other collision will pretty much be the same. And of course, this is ideal gas law. We do not factor in gravity, we do not factor in whatever the particle could look like, just a simple sphere. So when you have this collision, it will also be an elastic collision, alright? So those are some of the things that you will have to consider. Now, since it moves towards the x direction and collides with the wall, now how about we find the force that you have in this collision? So, Fx, alright. What is so special about Fx? Now, Newton's second law, force is equal to mass times acceleration. What can acceleration be? You can change it into the first derivative for velocity, if you're talking about instantaneous acceleration, that is. But then you also have the acceleration over a period of time, where you can use the difference between your velocities, initial and final, or initial and terminal, and you divide by the time taken, which you can use that, which here, let's say the time taken is tau, alright? So what will your m times the difference in v be? So m would still be m. Now v, what would be so special about v? So v, let's just say we have an initial velocity and a terminal velocity. But since this is an elastic collision, the magnitudes will be the same. The direction isn't though. So an initial velocity and a final. So you need to use a final to deduct the initial, alright? So if you could find it quick enough, and by this graph over here, in this kind of coordinate system, you can take this direction as positive x, alright? So that means the terminal velocity will be in a negative direction, which gives you negative 2 m v x I, alright? Okay, so this is just a simple one-line formula, but there are quite a number of things that you have to clarify with. Firstly, do you always have to use x? No, you wouldn't always have to use x, but if you use x, the rest of your procedure need to use x. You can use y, but the rest of the things, you will need to use y. Of course, you can also have positive, negative, but in what cases would you have positive and negative? Now if you look at this, since this is a negative, which is in this direction, can the particle really give a force in this direction? Well, this force here would actually be by the wall it bumped into on the particle, alright? So this is a force by the wall on the particle. If you want the force by the particle on the wall, then you just remove that negative, since this is Newton's third law, and in fact an elastic collision. So Newton's third law, every reaction you have an equal and opposite reaction, and since this is the ideal case, yeah, that applies. Now, is this really the only way you can think about it, using F equals ma? Of course, there are other ways that you can think about it, if you have learned it, that is, which is if you have learned impulse. Since impulse, you can equate it to the difference in your momentums. So that would be a similar thought process to F equals ma and the difference in its velocity. So the difference in velocity just becomes difference in momentum. And since it is elastic collision, well, the magnitudes are the same. Magnitudes, alright? So that is the first part we are going to see. You have to be aware this is by the wall on the particle, which of course later on you have to be very aware of your signs in order to not make any direction mistakes, alright? So this is the first thing. Now, do we have any other things we want to find? So how about the force, but this time it is an average force. So what is so special about this average force? Now an average force, that means you have to divide by this time taken. So how about we add them up from when it starts to when it ends, alright? But what are we going to add inside here? So that part would be an F. So you have an F equals ma, which let's just say we write this as ma, since we have the force from time to time, right? They could be different, they could be the same, it really depends, alright? So ma, what can you change the acceleration into? Yes, you can change it into the second derivative of your x, but what would that do for you? So how about let's take a look at its first derivative. Now what is that going to do either? So if you change it into first derivative, well of course m, you could also take it out. So first derivative, that means dv over dt. But what v are we looking at right now? So right now we are just looking at when it collides with the wall in the x direction, alright? So this is an x direction, and again dt. So how about let's change this up a little bit, where we will have m over tau and inside will be dvx. But what would your boundaries change into? So boundaries, they would actually change into your initial velocity into your final velocity or your terminal velocity. Alright, so that would be m over tau, so v, or your terminal velocity minus your initial velocity, which would actually be kind of the same as what you had just now, since the magnitudes are the same, but this would actually be in a negative direction. So you have negative 2mv, well you take the initial velocity, alright? Since generally, before you start an experiment, you want to take its initial velocity, not immediately take its final velocity and all, alright? So again, this is a negative, which is by the force by the wall on the particle, alright? You have to be aware of that. It will be in the negative direction. But of course, you can also change it around a little bit that it becomes positive, but that would really be up to you, whether you want by the particle on the wall, by the wall, by the particle. But of course, in the case of your pressure, you would probably want the particle on the wall. But but since this is an ideal case, it is really just a problem of positive or negative, which you have to be aware in the finals, alright? So that would become a problem, alright? So now that we have this for your average force, what else are we going to need? So other than this force, how about we have, let's say, we add in more particles. Now what happens if we add in more particles? The moment we add in more particles, that means we would need to find how much particles would be in that place at the same time, right? So then you have like a number of, let's say, colliding particles at the same time, or at a given time, or at a given place and time, whatever you like to think of it, alright? Now what would be so special about that specific range of place? So that would be, so you would need a dn over n, where n, this below n, would be your total number of particles within, alright? You have to be aware of whether you use a capital N or you use a small n, since this capital N here would be more of a total number of particles rather than number of moles of particles, alright? So with this total number of particles, what you will have here is kind of more like a percentage of how many particles will be there out of all of your particles. So what do you get from this part? Well, of course, you would also have a little place. So this little range, and in front would actually be your probability density function, alright? Which is an f v. Well, you could also write a v with a vector, up to you. So what is so special about this function over here? Well, this function is actually what we have in previous lessons. Now if you're curious to how do you find this function, where do you get it from, you can go back to previous lessons to check it out, alright? So this is where we can use a probability density function. Alright, what now? So we have these two parts, but are we really sure of how we can find that? Not yet, of course. So what else do we need to find? Now let's say we just take one portion of this out, and let's call that a tube, for example, or just another smaller container, alright, whatever you like to call it. So you would want to find the volume of that, right? So how are you going to find the volume of that? Now here we would need to use a few different other variables, alright? So these variables, of course, at last they'll come into play on why you would have to choose to use specific variables. So let's just say the volume. What would be so special about this volume? So volume, let's just say the cross-sectional area of your little tube across container, whatever you like. So that cross-sectional area across, it would be the A, alright? So, well, for example, you just have a little tube. So this cross-sectional area, you will have A, alright? So, cross-sectional area being A, what would you need? What else would you need? So of course then you will have like the height for it, isn't it? So this height, what can you use to find it? Now, in primary school, you probably have learned something like distance is equal to speed times time, right? Well, actually, we're kind of using something like that over here. Whereas we would be having velocity in the x direction, beware, x direction, we're not going to have like y direction or z direction, alright? And u times whatever time it takes, right? So this is going to be the so-called volume you have for your little tube. What else do we need? Well, you would also want to find your number of particles within the volume, isn't it? So, how do you find the number of particles? So you have a volume, and what else? So you have a capital N, right? Capital N, but that is the total number of particles. But can you somehow use that? Well, of course you can. So what we can use is actually, since you have the volume of whatever's inside here, if you have its density, you could use it to find the number of particles within that specific area, right? Or region, not exactly area, okay? So what we can use is N divided by, in this case, we have a V. V, which is the entire thing, not just restricted to the tube, alright? So this will be the number of particles you will have within the tube. Right. Is that it? Not quite. So we still need to take a look at a few other different things. Let's say, for example, number of particles within a specific region, or the number of particles colliding given the time and all, okay? So what would that give you? Now, of course, we would need a number of particles. Your total number of particles within the tube, well, you have N, A, V, X, tau over V. Beware, this V is your velocity, this V would be your volume, alright? So, what else would you be taking a look at? Now, since we want a little part of whatever you have, a little part, what do you think of? D something, right? Since that would be so-called infinitesimal. So how about let's take a look at this part over here. We could add that part on here, isn't it? Since then you will have the percentage of how much colliding particles you would have with the surface of yours. So we would put this on. Right, so this is what we will be seeing. Now, is this it? Right, so with all that we had, we can now finally find what is your average force on the surface. But what is so special about this average force on the surface? Didn't we already have one that is for your particle? Well, of course, we would have a lot more complicated for this section, since the different particles, there will be a different amount hitting at each time and all. So how are you going to find that? Using what we had before. Since just now, we did have one part, which is the number of particles striking your surface at a given time tau. So that is given by N A Vx tau over, so since this would be volume, sorry. So this is your volume. But of course you have to be multiplied by your probability density function. And then dVx, dVy, and dVz. Alright, so that is pretty much what we had. But of course, this is just the number of particles. Now you have to multiply by the amount of force each particle has. So the amount of force would be 2mvxi over tau. Does this look familiar? Well, of course it does. It is basically the first thing we had in this lesson. But of course, you will also have to be aware there would be no more negative, since this is now the particle exerting a force on whatever you have. And whatever do we have? we'll just take that as a little, you could call it a cylinder, you preferably would call it a tube with this A, alright? So then you could exert a force on, let's say, this side over here, okay? So this is what we will be seeing. Now, what can we find? First of all, we should take out the coefficients that will not be participating in this integration, just to make things a lot more cleaner and it looks simpler. So, what are some of the things? Those will be 2m and a. The two vx's will be inside, tau is cancelled out, and over v. Then you have to determine their boundaries. And inside you have vx squared, since vxi and vx are technically the same. And of course, your probability density function. Alright, so vx, vy, and vz. How are we going to determine the boundaries? Of course, you could take a look at the pictures you have again, the graphs you have again. Vx, how must it come in order to collide with the surface? Well, it has to move towards the surface, isn't it? So in order to move towards the surface, Vx has to be from 0 to infinity. Well, for Vy and Vz, why? Well, as long as Vx is positive, whether Vy is positive or Vy is negative would actually not matter. So for Vy and Vz, they'll both be from negative infinity to infinity. Alright? So next part, we already have the boundaries. Now, the only thing left would be your probability density function. Now, what is our probability density function? You would actually have it from the previous lessons. Square roots m over 2 pi kbt and then cube and e to the power of negative mv square over 2 kbt. And then dvx, dvy, and dvz. Right, so this is what we will see. Once again, we take out the coefficients that we do not need within this integration, whereas they will be your 2 pi kbt, of course. But beware, this v over here is actually velocity considered in all three directions. So you can use Pythagoras theorem to get Vx, Vy, and Vz for each of them separately. Alright? So we will take this entire chunk out. Now we can put each of them with their respective integrals, which makes them iterated integration. So let's say z, what are you going to have? You're going to have e to the power of negative mvz square over 2 kbt dvz. Alright, so this is the part you're going to see for vz and vy. Vy, I mean. And the last part for Vx, 0 to infinity, e to the power of negative mvx square over 2 kbt. But beware, here you actually have an extra Vx square, then dvx. Right, so you have these three different parts. So how do you plan on solving them? Well, of course, you could change their powers into squared. This entire thing squared, of course, the other parts having an actual square root, where you could actually take from outside to put them inside. So you'll be left with square root m over 2 pi kbt. At the same time, you could also take out 2 from two of them, which makes 4, which times 2 would be 8. Why can you take out 2 from each of them? Well, you just halve it, since if you recognize this type of functions, you might be able to realize this is pretty much a Gaussian function, which you can use for Gaussian integrations or arrow integrations, arrow functions, whatever you like to call them, alright? So the graph is actually symmetrical about the x-axis, which means you can halve them to take out the 2. Oh wait, we do actually have a pi down here, but we don't actually have a pi down here. So what happens when you have the extra pi? Well, they will just remain on the outside, actually. Alright, so here we have an extra pi, since both of these don't actually need the pi. Right, so this is what your first term will look like, if I'm not mistaken. Should be, alright? So the same goes to the second term. Integrate 0 to infinity e to the power negative mvy square over 2kbt d square root. I'm sorry, this vx is not part of it. Vz, I mean. Alright, so this is what it should look like. Is this correct now? Okay, so m over 2kbt, then vy on the outside. Alright, so this is what your next term will look like. Alright, so for the last term, a bit tricky, doesn't it look? But of course, there are different ways to solve it. But for this way, you could just actually put one vx inside. But what would the consequences of that action be? You would have an extra half. So an extra half, then you just come here and make this become 4. Alright, so this is what you are going to have. Now, Gaussian integral, that means this part here actually straight away you can make it become square root pi over 2 if you already know how to solve it, or you can go back to previous videos to find out why is this part actually square root pi over 2. Alright, so square root pi over 2. Now what are we going to see for this part over here? Well, actually, you repeat the same thing. Or do you? Yes, in fact you do. So what is going to happen? You're going to have to put in m over 2kbt with a negative, actually. So when you have to put this part inside, that means you have an extra, so I'm going to just write this step by step in case miss out anything. So negative, so that means you will need 2kbt over m in order to make this vx d e to the power negative mvx square over 2kbt. Alright, so this is what it should look like. Okay, so what do you think this part is going to use? This part here is actually going to use integral by parts. integral by parts. Alright, so there are some things that we can cancel out. Pi, 4. And of course you would want to try to simplify this part as much as possible too. So you're going to see negative square roots 2kbt over m pi. And then here you're going to have m and a over no more pi, just v. Alright? So, integral by parts. How are you going to solve this? Vx e to the power of negative mvx square over 2 kbt. This part you have to sub in 0 to infinity, while the other part would be minus integrate from 0 to infinity e to the power of negative mvx square over 2 kbt dvx. Alright, so that is the part where you're going to see it. Now, let's take a look at this part in front. You have infinity you sub in. There's actually infinity times 0. But this is actually still a 0. Why is that so? Well, of course, you could change this into a denominator, and then you just use L'Hopital's rule. Well, we won't be exactly showing that here, or it could be a bit longer, but it is actually pretty simple, right? You can try L'Hopital's rule on your own. Well, if you sub in 0, well, that's a 0 times 1. So it's 0, 0. So this part, we just don't care. Now, in this section, does that look similar? Of course it does. We're just going to repeat the same thing we did from above, again in this part. So, we are going to have negative square root 2kbt over m pi, and here we have m and a over v. Then you are going to have negative and another negative. That makes, so square root 2kbt over m. And the inside would be integrated from 0 to infinity e to the power of, well, of course you could choose to rewrite this entire thing, or if you already know, you could technically just directly write this as square root pi over 2. Whoops. So, square root pi over 2, again we could combine these two together to show, so, whoops, negative here. Alright, so combine these two and you're going to see negative 2kbt over m with a square root pi, m and a, well of course you can already cancel these two m's, over v times square root pi over 2. Alright, so this is a part where you're going to see over here. So you can cancel out the two m's, the square root pi, and the 2's. And it seems like this is what you are going to find. Wait, whoops, there is no negative in this part since this square is only this part, so that means this here is actually a positive. So a positive and a positive. Alright, so since this is the part that we're going to see, now what did we have originally over here? So there's an F. Now how can we change this thing? Now F, pressure, is force divided by area. So that means F, you just divide this A to the other side to find what you need, which is your pressure. And you multiply the V to the other side, so it becomes PV equals NKBT. And NKBT is actually just nRT. So this is proven. Alright, so this is pretty much the entire process in order to prove the ideal gas law. Alright, so I hope for this lesson it's pretty clear so far. Alright, so this is the entire integration process. Alright, so from the beginning you did require both your Newton's second law and your Maxwell-Boltzmann distribution in order to get the part you have over here. So I hope for this lesson you're clear of everything so far, and this is how you prove the ideal gas law by using the Maxwell-Boltzmann distribution. Right, so at first we did use the Newton's second law. Afterwards we moved into multiple particles. Well, in multiple particles we went step by step to find at last what you have for, let's say you're given a period of time, how many particles will be colliding into the surface at once. And then you change that part into the force, which is what you have over here. So that is pretty much all we have for this lesson, and thank you for your watching.